So we have now our second lesson in chapter 1, the Gaussian elimination and Gauss-Jordan elimination. We will start with an introduction to matrices. If m and n are positive integers, an m by n matrix is this rectangular array where these entries, aij's, are numbers. This matrix has m rows and n columns. And take note that we usually denote matrices by capital letters. The entry aij is located in the ith row and jth column. For example, this entry A32 is found in the third row and second column. Also, the index I is called the row subscript and the index j is called the column subscript. So again, these indices will tell you which row and column an entry belongs. Next, we have the size of a matrix. A matrix with m rows and n columns is said to be of size m by n. When the number of rows is equal to the number of columns, that is, m is equal to n, the matrix is called a square matrix of order n, and the entries A11, A22, A33, and so on are called the main diagonal entries. For example, this matrix is of size 1 by 1. This one is of size 2 by 2. And this one is a 2 by 3 matrix since we have 2 rows and 3 columns. Matrices are commonly used to represent systems of linear equations. The matrix derived from the coefficients and constant terms of a system of linear equations is called the augmented matrix of the system. Moreover, the matrix containing only the coefficients of the system is called the coefficient matrix of the system. For example, given this system of linear equations, its corresponding augmented matrix is this one. We write the coefficients of this system in the first 3 columns. So we have 1, -1, 2. We have -4, 3, 0, and then 3, -1, -4, and then we write the constant terms in the last column. On the other hand, its coefficient matrix is obtained by writing only the coefficients of the system. Now we have the elementary row operations. These are almost the same with the operations that produce equivalent systems which were introduced in the previous lesson. So we have interchange 2 rows, multiply a row by a non-zero constant, add a multiple of a row to another row. We note that an elementary row operation on an augmented matrix produces a new augmented matrix corresponding to a new but equivalent system of linear equations. Also, 2 matrices are row equivalent when one can be obtained from the other by a finite sequence of elementary row operations. For example, if we interchange these 2 rows, row 1 and row 2, we get a matrix which is row equivalent to this one. And the corresponding system of the new matrix is equivalent to this given system. Now, to keep track of each elementary row operation you perform, it would be helpful if we use a shorthand method of notation, such as we have in interchanging the first and second rows, we use this notation. So we use double arrow to mean that we interchange row 1 and row 2. So in here we have 0, 1, 3, 4 as row 1, and then we have 0, 1, 3, 4 here as row 2, and then our row 2 here becomes our row 1 here. Also, another example, we have multiplying the first row by 1/2 to produce a new first row. So we use this notation, so a forward arrow. So again, we multiply row 1, R1, by 1/2 to produce a new R1, or first row. So we just copied the rows 2 and 3 here. We only change row 1 by multiplying by 1/2. So 2 times 1/2, that becomes 1. Negative 4 times 1/2, that's negative 2. And then 6 times 1/2, that's 3. And then negative 2 times 1/2, that's negative 1. Okay, so again, we use this notation. Also, another one, we have, if we add negative 2 times the first row to the third row to produce a new third row, we use this notation. Again, we multiply R1 by negative 2 and we add it to R3 to produce new R3. So since we want to produce only new R3, we copied R1 and R2. So we have here. And then to yield a new R3, we multiply R1 by negative 2 and then add it here in row 3. So that's 1 times negative 2, it's negative 2 plus 2. So we have now new entry here, which is 0. We multiply this by negative 2, so that's negative 4 plus 1, so that's negative 3. And then negative 4 times negative 2, that's 8, and then plus 5, so that's 13. And then times negative 2, this is negative 6, and then plus negative 2, so that will become negative 8. So these are just some examples of the notation that we can use to denote these elementary row operations. Now, to give you some more examples, let us solve this system by applying elementary row operations to its augmented matrix. So we have here the given. First, we write the associated augmented matrix of the system. So we copy the coefficients and the constant term. So we have 1, negative 2, 3, 9, negative 1, 3, this means 0 here, negative 4, 2, negative 5, 5, 17. Okay, so this is the augmented matrix of this given system. Next, we add the first row to the second row to produce new row 2. So again, we want to produce new row 2, so we will just copy row 1 and row 3. So we use this notation. We have R2 plus, that's plus R2 plus R1 to produce new R2. So we will just add these two rows to produce new R2. We copy the first row. So we add this becomes 0. It's negative 2 plus 3, that's 1. 3 plus 0, that's 3. And then 9 plus negative 4, that's 5. Again, we copy rows 3. Then we add negative 2 times the first row to the third row to produce a new third row. So that is, we want new R3, so that is plus negative 2 R1 to produce new R3. Okay, since we want a new R3, we will just copy the first two rows. Sorry. So again, to produce new R3, we multiply the first row by negative 2 and then we add it to row 3. So this 1 times negative 2, so that's negative 2 plus 2. So this becomes 0. And then we multiply this by negative 2, so that is 4 plus negative 5, so that's negative 1. We multiply this by negative 2, so that is negative 6 plus 5, so that's negative 1. And then times negative 2, this is negative 18 plus 17, so that's negative 1. Next, we add the second row to the third row to produce a new R3. Again, add the second row to the third row to produce a new R3. So that would be copy the first two rows since we will have new R3 only. So we have 1, 3, 5. And then we add this 2, so that's 0. We add this 0. 3 plus negative 1, so that's 2. Then 5 plus negative 2, that's 4. Lastly, we can multiply the third row by 1/2 to produce new R3. So that is multiply the third row by 1/2 to produce new R3. Okay, so copy the first two rows. 3, 9, 0, 1, 5. Then multiply by 1/2 the third row, so that is 0, 0, 1, and then 2. Note that we can write the corresponding system to this new matrix. So we will have this column represents the x, we have the y, the z, and this one is for the constant term. So we can have so we have 1x, or just simply x, negative 2y plus 3z equals 9. And then we have this for y plus 3z and then 5. Then 0 for x, 0 for y, so we have for z only here. So we have z equals 2. Recall that this system, this system is in row echelon form. And we can solve this system by back substitution. So we have okay, so we substitute the value of z here in the second equation. So that would be y plus 3 times 2 equals 5. So y is equal to negative 1. And also for the first equation, we substitute the values of y and z. It's negative 1 plus 3 times 2 equals 9. So that means this is 2 plus 6, so that's 8. So 9 minus 8, so that is 1. Thus, the solution to the given system is x equals 1, y equals negative 1, and z equals 2. Please note that this last matrix here is in row echelon form. To be in this form, a matrix must have the following properties. We have any rows consisting entirely of zeros occur at the bottom of the matrix. For each row that does not consist entirely of zeros, the first non-zero entry is 1, which is called a leading one. For two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. A matrix in row echelon form is in reduced row echelon form when every column that has a leading one has zeros in every position above and below its leading one. To make this clear, we have a following example. So we determine whether each matrix is in row echelon form. If it is, determine whether the matrix is in reduced row echelon form. So first, is this in row echelon form? So observe that we have the stair-step pattern here, and also each row has leading one. So that means this matrix is in row echelon form. Now the question is this in reduced row echelon form? The answer is no, since there are non-zero values above the leading one. For example, this leading one here, we have non-zero entry above it. Also, this leading one here, we have non-zero entry above it. So therefore, this one is not in reduced row echelon form. Next, this one is not in row echelon form, since the row consisting entirely of zeros does not occur at the bottom of the matrix. So this one. Next, for letter C, so this matrix is in row echelon form, but not in reduced row echelon form. Again, because there are leading one whose entries are non-zero above it. Next, this matrix is in row echelon form and in reduced row echelon form. Notice that the entries above and below each leading one are zeros. So this leading one, we have zeros below it. We have leading one here. Above and below this entry are zeros. Also for this one. So this one is again in reduced row echelon form. Now this matrix is not in reduced row echelon form. Why? Since in the second row, the first non-zero entry is not 1. Okay, so take note, we must have a leading one. So therefore, this is not in row echelon form. And lastly, we have this matrix. So this is in row echelon form and in reduced row echelon form. Okay, so again, the matrices A, C, D, and F are in row echelon form, and the matrices given in D and F are the ones that are in reduced row echelon form. Now let us discuss the Gaussian elimination with back substitution. The steps are the following. First, we write the augmented matrix of the system of linear equations. Next, we use elementary row operations to rewrite the matrix in row echelon form. And then we write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. So for example, we solve this given system. So what we do first is we write the augmented matrix of the given system. We have 0, 1, 1, negative 2, negative 3. We have here 1, 2, negative 1, 0, 2, 4, 1, negative 3, negative 2, 1, negative 4, negative 7, negative 1, negative 19. So again, take note, this is the augmented matrix of the system in which we just copied the coefficients of the system, and this one corresponds to the constant term of the system. Next, we want our first entry in the first row to be 1 so that we may interchange row 1 and row 2. So we have interchanging row 1 and row 2, we use double arrow. So again, we only interchange rows 1 and 2. So we have here 1, 2, negative 1, 0, 2. We have 0, 1, 1, negative 2, negative 3, and then we copy rows 3 and 4. Then our next target is the entries below this leading one should be 0. So to produce a new third row, we will multiply the first row by negative 2, and then we add this to the third row. That is, we have, again, we multiply the first row to the to negative 2, and then we add to the third row to produce new third row. So we want a new third row, so we copy rows 1 and 2 and then 4. Again, we multiply this by negative 2, and then we add to this. So times negative 2 plus 2, so that's 0. Again, this is our target, to make this entries below 1 to be 0. So times negative 2 is negative 4 plus 4, so that is 0, times negative 2, so that's 2 plus 1, so that is 3, times negative 2, so that's a 0, plus negative 3, that's negative 3, times negative 2, so that's negative 4, plus negative 2, so that's negative 6. Then we copy the last row. 7, negative 1, negative. Also, we want this to become 0. So to do this, we multiply row 1 by negative 1 and then add to row 4. To produce new R4. So we multiply this by negative 1 plus 1, so it's 0. Multiply by negative 1, that's negative 2 plus negative 4, so that's negative 6. Multiply by negative 1, so that's positive 1, plus negative 7, so that's negative 6. Then multiply by negative 1 plus this 1 times negative 1, so that's negative 2 plus negative 19, so that's negative 21. Next, we have here a leading one. So we want the entries below it to be 0. So to make this 0, we can multiply this by 6 and then we add it here. So that means we will multiply row 2 by 6 and then we add it to row 4. That is that must be 6 times row 2 and then to yield new row 4. Okay, so we have copy the first row 1 0 2 0 1 1. We just want a new row 4, so we will copy the rest of the rows given. So we have 0 0 3 negative 3 negative 6. Okay, so again we will multiply this row by 6 and then we add it to row 4. So times 6 plus this 1, so this is 0, and then times 6 plus this 1, so that is also 0. Multiply this by 6, so that's negative 12, plus negative 1, so that's negative 13. Multiply by 6, so this is negative 18, and then plus negative 21, so that's negative 39. Next, we want a leading one for each row. So this third row, we have none this is not 1, so we have to make this 1. So to do that, we can multiply row 3 by 1/3 to produce new R3. Okay, so we multiply by 1/3, so this is 1 now. That is -1, and then we have -2. Okay, next, we want this to be 1. We need to have a leading 1. So to do that, we multiply row 4 by -1/13. Row 4, or simply divide by -13 to produce new row 4. Okay, so we have here 0, 0, and then this becomes 1, and then multiply by -1/13, so therefore that is +3. So this matrix is now in row echelon form. So we now write the corresponding system and do the back substitution. So the corresponding matrix, the corresponding system to this matrix is we have x plus 2y. Oh, sorry, we use x sub 1. So we have x sub 1 plus 2, x sub 2 minus x sub 3 equals 2, and then we have x sub 2 plus x sub 3 minus 2 x sub 4 equals -3. We have x sub 3 minus x sub 4 equals -2, and lastly we have x sub 4 equals 3. Again, to solve this, we'll use back substitution. So we substitute this value of x sub 4 here. So we have x sub 3 minus 3 equals -2, which implies that x sub 3 is equal to 1. Also, we substitute these values of x sub 3 and x sub 4 to the second equation to get the x sub 2. So this is 1 minus 2 times 3, which is equal to -3. This implies that x sub 2, this is -6, -7, we transpose that one, so x sub 2 is equal to, right, so this must be +1. Sorry, this should be +1. So this is -6 plus 1, so that's -5. We transpose that one, so -3 plus 5, so that is 2. And then lastly, for x sub 1, we substitute the values of x sub 2, x sub 3, and x sub 4 to the first equation. So 2 times 2 minus 1, which is equal to 2. So x sub 1 is equal to, this is 4 minus 1, so that's 3. Transpose that one, so that's -1. Thus, the solution to the system, we have x sub 1 is -1, x sub 2 is equal to 2, x sub 3 is equal to 1, and x sub 4 is equal to 3. Okay, so we got the solution by Gaussian elimination with back substitution.